So in this next webinar, we're going to talk about contracts and the contract code. It's a relatively short webinar because contracts in Corda are actually quite simple, as you will soon find out. So the whole point of Corda is to bring potentially distrusting parties into consensus about shared facts. In the previous webinars, we discussed state sequences, as well as transactions, which are atomic units of change to the ledger. But what we haven't discussed yet is how actually these state objects or these shared facts evolve in a way that is valid, that all parties agree on. And for that, we need some contract code. We need a way to verify whether a proposed transaction is actually something that meets the rules. And these rules or constraints are defined within the contract as a function, as you'll soon see. We need to introduce a way such that all of the parties on the ledger can objectively reach consensus about whether a specific transaction proposal is valid or not. And that's what we're doing here with the contract code. With states, you'll note that they only contain data. Of course, you can have some helper functions as well, but typically you can think of states as just a schema, a Java class with a bunch of properties, and you can assign values to those properties. As the state changes or transitions over time, then these properties change. We need a function that we can apply over the change in state to ascertain whether it's a valid change in state, and that's exactly what we're doing with the contract code. If we take a closer look at state objects, we've got some properties. Those are just the properties that I mentioned in the previous slide. So they're the attributes of whatever object we're looking to model with Corda. Then we've also got the participants list. The participants list concerns who can consume or use this state in a valid transaction, and typically they're the parties to the agreement or the owner of some instrument, for instance. But then, as well as that, we also have a reference to some contract code. This contract code is what defines the verification function, as we'll soon see. And this is actually a diagrammatical version of a state in Corda. There's a contract state interface. It's actually implemented exactly like this. This reflects exactly how states are represented in Corda. And each state will reference a contract. The contract can be implemented in any way that the developer wishes to. You can even have an empty contract that doesn't do anything, that will just validate any states. But more often than not, you'll think long and hard about what constraints you want to put in your contract code such that your states evolve correctly over time. Transactions, as we've seen in the previous webinars, they can be quite complicated. They can contain many types of states. You can split and merge states. You can have state issuances, updates, and exits within a transaction as well. But most importantly, you can have multiple types of states, and that's what this diagram shows here. So we have a transaction where presumably a cash and a bond is being swapped. And to ascertain whether that's a valid transaction, we need to use both the bond and the cash contract. So firstly, the bond contract is probably the most important one here, because the sale of the bond needs to reference the cash. The contract code inside the bond contract would reference both the bond and the cash state objects to ascertain whether the bond trade is valid. And then the cash contract is much more general, and the cash contract typically won't reference other contracts. But what it will do is ascertain whether a cash payment is valid. So are the right digital signatures being collected from the right parties, i.e. the current owner of the cash, for instance. Importantly, what this diagram shows here is that states reference a contract, and then those contracts are used to validate the transaction containing the states. And you can have many state types inside a contract. Here there's two, but you can have as many as you need to fulfill your use case. Moving on to the contract code. The contract code is really just a very simple function. You can see here down below we've actually got some Kotlin code here. We see the fun keyword, which means you're defining a function. It's called verify. It takes one parameter called transaction, and it returns a unit, which is essentially just a void like in Java or C. So it doesn't return anything. And what the verify function does, it will execute all of the constraints which the Corda developer has defined. If any of those constraints, given the input transaction as the parameter, if any of those constraints fail, then the verify function will throw an exception. If all of the constraints passed, then the verify function will not return anything at all, and thus the transaction that was passed in as a parameter to the verify function will be considered valid for that contract. But of course, as many contracts can be referenced inside a transaction, all of the verify functions need to pass for all of the contracts referenced. These next couple of slides are just a quick point on pureness of the verify function and that it needs to be a deterministic function. So the reason why is that for each time we verify a transaction, we need to get the same results. So the verifications might be performed by different peers on the network, and they might be performed at different times. So we need to ensure that the contract code is deterministic. So for a particular given transaction, it always returns the same result. And we need to do a couple of things to the JVM, the platform that the smart contract sandbox runs within, to ensure that it is actually deterministic. So there's a bunch of things that you obviously cannot do with a deterministic contract. One of those is use a random number generator or potentially referencing data external to the ledger that may change, or more importantly, referencing it in an uncontrolled manner. Because potentially the changing data or introduction of randomness into the contract could change the result, and thus you'd have side effects. And this would significantly undermine the integrity of the ledger. What we do is we execute the code within a sandbox. It's a modified version of JVM. It has a whole bunch of features stripped out, and we've whitelisted the functions or the methods which the sandbox is allowed to use, or which Corda app developers are allowed to use to verify their contracts. There's a whole bunch of other things that I won't cover here because this is a relatively high-level webinar, but you can read more about the smart contract sandbox in the Corda technical white paper. But suffice to say that the contract code needs to be deterministic. It needs to be a pure function, because each time we run it, we need it to return the same result given the same input. So now just looking at some examples of contract code. These are very trivial, simple examples, but they should give you a flavor of how you would write your contract. So we've used some pseudocode here. It kind of looks a bit like Python, but it should give you a good idea of what you can do with contract code. So I like to think of there being two types of contract constraints. The top two, I say, are structural constraints around how the transaction is structured. So here we're saying that the transaction should have no inputs and one output. So typically, these are constraints that you put for an issuance transaction where you're issuing one new state onto the ledger. If you pass in a transaction that does have an input or has more than one output, then that transaction would not verify. The verification function in this case would throw an exception for that particular transaction. Then at the bottom, we've got some constraints over the properties of the states within the transaction. So here we're referencing output 0. So as it's number 0, that's the first state in the outputs list, and there's only one state here because the output's size is 1. This is the only state that's been created, and we're just checking inside this state that the lender is not the borrower. So presumably the lender and the borrower fields are either public keys, or there's some wrapper object around a public key. And we're just checking that those public keys are not the same. So what we're saying here is that the lender can't lend money to himself, or the borrower can't borrow money from himself. So it's just a very simple constraint. Lastly, we're just checking that the amount, this is presumably an IOU, and we're just checking that the amount is always greater than 0, because it doesn't make sense to issue a 0 IOU onto the ledger. It would have no purpose. Typically, constraints are just checks or Boolean expressions, and you can have as many of them as you want inside the contract code, and they can be as complex as you like. I mean, you can run complex algorithms to determine whether some property of an input or output state meets certain criteria, but ultimately the return value of your expression needs to be a Boolean value. And then, of course, all of these expressions need to be true for transactions to pass verification. That's it with the contract code, really. It's really quite simple. And I'm sure you remember from the previous webinars that in Corda, transactions are proposals that require verification, as opposed to being instructions that are carried out by all the parties on the network. So this is where the contract code comes in to verify these proposals. So all parties on the ledger would typically have access to the same contract code, and they would get the same result, because the contract code is deterministic and it's run in a deterministic environment. So they will all be able to objectively ascertain whether a transaction is valid or not. So just to recap, the contract code is a pure function executed in a deterministic environment on a need-to-know basis, and the contract code is what verifies transactions and determines whether they are valid updates to the ledger or not.